Hello, I'm Bruhns, and together with Samira Briongos, I will present our work, Aim, Wait, Shoot, how the CACHESNIPER technique improves unprivileged cache attacks. This is a joint work with Pedro Malagón, Thomas Eisenbarth and José Moya. In traditional cache attacks like flash and reload or prime and probe, the victim at some point performs a secret-dependent access to data or a secret-dependent instruction. In our example code, this happens in line 5, where the victim performs a secret-dependent access to table. This gives an attacker the opportunity to remove table at the point secret from the cache, wait for the victim to execute, and then look for table at the point secret in the cache. If it's in the cache, the victim has used it, and if not, the victim has not used it. Therefore, the attacker can infer the value of secret from the occurrence of the table in the cache. One possible countermeasure against this is prefetching or an always load strategy. As you can see in line 4, we added the blue box where we always load the table into the cache. The idea is to ensure that the entire table is always available in the cache. This makes it harder for the attacker to know if the table at the point secret is in the cache because the victim used it or because of the prefetch. It's an easy to implement countermeasure, and it's applied in different cryptographic libraries. However, as you can see, it does not remove the secret-dependent access to the cache from the code. This means that an attacker still has a window for attack in prefetch-protected implementations. This is our setup. We have an attacker and a victim who both work on the same machine. This is the only assumption that we have. Both can have user-level privileges only, and they don't need any further synchronization than what we present to you. The attacker challenges in the scenario are: the attacker needs to detect the execution of the target algorithm when the victim starts it. She needs to find out the exact state of the target after she detected it. She then needs to find out how long she needs to wait until the data is prefetched. And then she needs to evict the target data from the last level cache at exactly the desired instant, which is after the prefetch but before the actual utilization. To tackle the first two challenges, we tested a flash and reload, a prime and probe, and a TSX abort approach. TSX abort uses intertransactional memory. As you can see from the graph, TSX works best for synchronization because it detects the victim's execution with high probability, and it makes a very narrow peak, meaning that the detection is always in nearly constant time. For detecting with TSX, we first load data that maps to the same cache region as the victim's code into a transaction. As soon as the victim starts executing, our data will be removed from the cache, which will cause our transaction to abort. We can then wait for the abort signal, and since that always comes at the same time after the actual abort, we know which state the victim is in when we receive the signal. As you can see from this graph, we tested against various noise benchmarks. The dark blue bars show our baseline, so there you can see that we detect the victim's execution in almost 100% of all cases, but even with all the noise benchmarks, we still detect the victim's execution in at least 75% of all cases, which is more than enough for an attack.
So as soon as the abort signal is received, the attacker knows exactly which operation is the victim executing. And if she has profiled everything application in advance, she knows exactly for how long she has to wait before the data is prefetched into the cache. At this point, she just needs to find a way to remove from the cache the data that has just been prefetched. If there is a memory, this can be easily done just by using the CLFlash instruction. But if not, we have found a way to remove that data from the cache with what's just single access. And this is possible because on the one hand, we know which is exactly the replacement policy of the last level 3 cache, and on the other hand, because transactions are really transactions. That is, any data that is placed into the cache during the transaction stays into the cache even if the transaction aborts. That is, if we assume that we have cache set as the one depicted in this figure, the order of the eviction of the elements in case of conflict will depend on two facts. On the one hand, the ages of all the blocks, and on the other hand, on the location of each of the blocks. So we need to make sure that the element that has just been prefetched automatically becomes the eviction candidate. In order to do that, one can just access the blocks B to H to ensure the ages of all of them is reduced. At this point, if the victim accesses the target T2, even if the ages of B to H increase, T2 automatically becomes the eviction candidate. That is, if the attacker correctly prepares the transaction once the abort signal is received, she can just access A and remove the data that has just been prefetched into the cache. We have used this technique to successfully retrieve the secret key of the AES Xbox implementation of OpenSSL. This implementation prefetches into the cache the whole Xbox before executing each of the rounds of the encryption algorithm, and by targeting the last round of the encryption algorithm, we have been able to successfully beat the data from the cache and therefore retrieve the secret key using around 500,000 samples. We have also tested this approach against the popular T-table implementation and shown that further control of the eviction implies a reduction on the number of samples required to retrieve the secret key. We have also tested this approach against an RSA implementation of WolfSSL. This implementation is a modification of the popular square and multiply algorithm that always executes the multiply operation. The problem is at the end of the multiply operation, or even with the reduction function, it accesses one cache location that is depending on the value of each of the secret bits of the key. As a result, we have been able to successfully identify around 90% of the secret bits of the key. In conclusion, prefetching does not work as a countermeasure against cache attack because even an attacker with no privilege can still retrieve secret information from the cache from applications protected using this kind of countermeasure. To do that, the attacker just needs to find a way to synchronize its execution with the victim, and TSX works pretty well to achieve that synchronization. And after that, she just needs to find a way to remove the data from the cache that has just been prefetched. As we have shown, we can do that with just one single access. So if she aims or prepares the X scenario for the attack, then waits and then shoots at the cache at the right moment, she will be successful in retrieving secret keys from its victim, as we have shown against AES and RSA. So that's all. Thank you for your attention. I just want to mention that in case you are interested, we have released a proof of concept of this approach in GitHub. Here's the link, and we will be happy now to take all your questions.